Okay, thank you. Thank you for coming and thank you for your donations. As Stefan said, they're going to an important cause. So today, we celebrate humanity's positive achievements. So I know I said certain things in the advertisement for this thing, although you should never believe what they say in the advertisement. So mostly I'm going to talk about the positive side of the story today. I'm going to tell you about how we learned to combine quantum mechanics and relativity together, and the change that happened in our perspective of the world when that combination happened. And because there's a lot of journeys to be taken, I think that it's much better to remind you, although I've given here lectures about relativity, and I've also given a lecture here about quantum mechanics, I want to remind you, of course, like what those things are about. So first we're going to talk a little bit about relativity, and then we're going to talk about quantum mechanics, then we'll take a break, we'll breathe out, meditate a little bit, and then we come back with and try to put them together. Okay. The approach that I'm going to take today is a little bit unusual in the sense that very often when people talk about various physics ideas and phenomena, they talk about what's out there. They take very much the experimentalist perspective of the world. They say, oh, these are the things that are happening out there. These are the phenomena. The experimentalists measure certain things and they find that certain types of behaviors, interactions occur in the world, and they think about the world in terms of what is going on, like what can we measure, what can we characterize. But I'm going to being a theorist, I'm going to give you like a theory perspective of the world. The theory perspective of the world is a little bit different. Yes, of course, theorists care about what's actually out there. They want to know what's going on in the world. They want to build sort of models of reality, mathematical models of reality, but they kind of ask a question that is a little bit different because they're not really exactly interested only in what's out there. They're kind of interested in generally what are the rules of the game. So when theorists think about the world, they're always messing with equations, and they're really trying to ask, well, how constrained are these equations? What are the principles guiding these equations, and can I mess it up? What happens if I add this here or that there? Can I tweak things? What constrains the kinds of things I can write down? So they're not just interested in what's out there, but in some sense they're interested in the space of possibilities because they're always trying to invent something else, right? So they're trying to figure out if we add something new, does that new term that I'm going to add to an equation, is that term going to insult anybody, or is that term going to be okay with the community, right? So is there kind of a principle, a cherished principle that would forbid a particular term or not? So in that context is really kind of the way that I want to discuss this subject, specifically because the space of possibilities when you combine quantum mechanics and relativity changed very, very dramatically. So that's kind of the idea. So quantum mechanics by itself didn't have this change. Relativity didn't have this change. But when the two combined, essentially the kind of rules of the game changed very, very dramatically. So that's generally the path we'll take today. Please ask any questions, interrupt me at any point. This is why I'm here. Okay, so we're going to be interested in always asking the question, well, we write down some equation, how unique is it? What are the principles that guide this equation? So this is what I'm going to call the theory perspective. So we're going to be interested in the theory view of the world, which basically always asks, what are the constraints on some set of laws? Sort of what are the principles? That govern some particular set of laws? What could I mess with, basically? Okay, so that's kind of the general perspective that we'll keep coming back to. So let's start our journey. First, I want to tell you about relativity and the structure of the equations that describe relativistic theories. But before that, I want to take a step back and just, give credit to Newton. Because Newton was an important intellectual step in our understanding of the universe. Newton said, to quote, I guess, the Big Lebowski, "This ain't nom, there are rules." That's basically what he said, right? So there are rules. He was the first person to kind of say essentially that, well, nature isn't random. There is some sort of mathematical model that we can write down for the world. And in particular, the model that he explained is gravity. So Newton's claim to fame is he essentially wrote down a model, a math model for gravity. And by doing that, he astounded everyone because he literally unified heaven and earth. He wrote down a law for gravity that described both how planets, like the moon, or go around the earth, or the sun, the moon or the earth going around the sun. So at one point, so both the equations both contain the truth of how the motions of the planets work, but also explain phenomena on Earth, like the fact that things fall, right? So he was able to unify those things and to precisely perform this magic to unify heaven and earth. He had to invent calculus. So to understand, to write down a law and show that that law applies here on Earth, but also for the planets, he invented calculus. Okay, good. So that's great. It's awesome that there are mathematical models of reality. So he was maybe the first to sort of try to put together such a model. But just because they're mathematical models of reality doesn't mean necessarily that there should be some fundamental framework or some universal framework to understand what the universe is. For example, you can think about economics, right? There are many mathematical models for things that happen in the economy, but there isn't like this universal framework for everything economical. Biology is another thing that we understand better and better, and we come up with more and more sophisticated mathematical models for, but there isn't some universal principle of biology that we know of yet. Maybe we'll discover it, maybe we'll discover some deep universal principle of economics and everyone will make a lot of money or lose a lot of money immediately, who knows. But physics is very different. Physics is different because there is kind of a fundamental underlying principle, something that really suggests that you should look for a universal framework, something that suggests that there might be principles that apply to everything. And so maybe I ask you first, what is a quantity that you could think of in nature that is universal and seems to apply everywhere, that kind of gives you a hint that maybe there is such a framework, that there's such a thing that you could talk about everything?
Energy.
Energy. Great. Energy. Energy.
That also pass.
Right? It's an amazing thing. It took people a long time to understand this, that in fact there's a universal concept which applies to all physical systems. And that's the idea of energy. It's something that is great that you have an intuition for. It's something that we're very familiar, but it wasn't a journey. It was a very difficult journey to try to figure out if that's in fact true. And so I want to tell you first of all an important consequence. Indeed, it's true that everything can be written in terms of energy. Moreover, it's not just that this is kind of the seed. It's actually true on a technical level. What do I mean by that? What I mean by that is that all physical quantities in nature can be expressed in units of the following. Length, so let's say meters. time, let's say in seconds, or whatever unit of time you want, and then energy, which you can, I don't know, physicists prefer joules, maybe given your personal struggles, you prefer calories, whatever. Whatever as the unit of energies that you find most appealing, this is it. Every quantity in nature can be expressed in terms of length, time, and energy. Like all these other units you've heard of, like, I don't know, current, volts, blah, 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 Celsius, Fahrenheit, they're all this. There's nothing else, right? And that's precisely the statement that energy is universal. Why does it have this structure? Because this is like the stage, right? This tells us where things happen and when things happen. So this is kind of, we live in space and time, we actually live in space-time. And question?
Yeah, what about mass?
Mass is described in terms of energy and length and time. So you could exchange this for mass. In fact, mass, of course, is the same as energy because of mc squared. Energy and mass are related to each other, but exactly, very good. So we could have used kilograms here, but in a sense, the reason this is true, that you can use mass, is precisely because actually it's energy. So there's no difference. So essentially, there's a stage. Events happen in our lives. They happen somewhere and at some time. So we need length and time. But what's amazing is that the only other quantity we need is energy. So the entire dynamics of a system, basically, if you want the script of what's supposed to happen, is just written in terms of energy. Okay, so that's the first big kind of unifying truth that suggests that there must be some kind of framework that describes the whole universe, right? It basically says, okay, energy is the key, and it's something universal. So I want to say a few more words about this, just so we have a sense of how this works. So basically, how do physicists think about energy? The way they think about energy is that the following. So I'm going to give you, again, kind of a theorist perspective. So there's dynamics. That's sort of, dynamics is what physicists call what happens. So this is what, this question of what happens, what's going to happen is the dynamical information. And so the dynamical rules, in the kind of from the perspective of modern physics, is that I have a system of some sort, and it has many configurations. For example, it could have molecules that are sitting here or there or everywhere. They're moving, they're doing something, or some other more complicated system. So a system has many different configurations. Now, once I assign to each configuration of that system an energy cost, I'm done. That's it. That's all I have to do. So now systems can negotiate with each other. They can exchange energy. Energy can come in, it can come out. But the entire set of rules of the game basically are about saying, well, this kind of configuration of the system costs that much in energy. So energy, you can think of energy as a kind of universal currency, and then different systems negotiate this and exchange energy. And by knowing which configurations are expensive in energy and which ones are cheap, I know how the systems will rearrange themselves, like what's going to happen. Okay. And a related idea, so what is kind of an indirect, bit of evidence that tells us that energy is like everywhere. Like say you weren't sure, what is this thing made of? Like maybe it has weird other rules, like maybe the stove behaves in a completely different way. What is kind of an indicator from our perspective that energy makes sense in any system independent of what it's actually made of, because we don't always know what everything is made of. And this is one of the crowning achievements of 19th century physics, is they figured out what is temperature. So people weren't sure what temperature was. They felt hot, they felt cold, they had thermometers. Of course, people understood that somehow temperature is important, but they didn't have kind of a really fundamental microscopic understanding of what temperature was until they started thinking about it, and until a discipline of physics emerged called statistical physics, where statistical physics was trying to understand how do many, many objects exchange energy. And what people understood was a very deep idea that temperature, which I remember, of course, in our life is measured in Celsius or in Fahrenheit or in whatever unit you want. Temperature is energy. In fact, what is temperature? It's basically just the average energy of a component of the system. So for example, if you take the energy of the gas in this room and you divide by the number of, let's say, molecules of gas, what you get is the temperature. That's what the temperature is. It's the average energy of a particular component. And precisely because that's what it is, it's kind of clear that if something has a temperature, like if I measure a temperature of something, and I have a framework, or I have different thermometers, and they all agree about the temperature of something, that basically says that they agree on the average energy of the components of the thing, which means that essentially energy makes sense. Even though I don't know what that stove is precisely made of, because it has a temperature, a well-defined temperature, I'm indirectly saying something about the stove. I'm saying that if I took all the basically fluctuations of all the different molecules in the stove, then on average, the energy per molecule is the temperature. So even though we measure this in Fahrenheit or we measure this in Celsius, really fundamentally temperature should be measured, whatever, in calories. So that's kind of a deep idea that took people a long time to understand. So, okay, good. Questions before I start talking about special elements?
Here's a question.
Yes.
So the temperature of the stove, you mean as an object, it's going to be at a certain temperature, right?
Right.
But it might feel cold right now if the room is cold.
Right.
It might get hot if the room gets hot.
Right.
So how does that relate to what you're saying? Are you talking about the intrinsic temperature of the stove?
It has no intrinsic temperature,
Okay.
because exactly what you said, it's in contact with the environment. So when something is, say, hot, its molecules have more energy than the environment around it, and they begin to leak that energy into the environment until the environment begins to heat up a little bit, and until they reach equilibrium. So that on the average, every molecule of gas that makes contact with the stove is about the same energy as every molecule inside the stove, on average. Great question. All right, good. So we have a framework. This is how we're going to try to understand the world, is through energy. And well, of course, you can be a sneaky kid and be like, yeah, but why does energy make sense? Where does energy come from? Hold on, we will answer that question. All right, so our first task is to think about relativity. So what are the rules of special relativity? So we'll talk about. So special relativity is the idea that two observers who are moving with respect to each other at a constant velocity, that they should have a way of essentially translating their lifestyle to each other. So everything that happens to one observer has an analog for the other observer, and they have to essentially agree on all the fundamentals. So all observers. So if you are sitting in a car but moving at a constant speed, and someone standing by the side of the road, you have to agree on kind of what happens. There must be a dictionary that relates what you see in the world. So all observers moving at a constant, it's important that it's a constant speed with respect to each other, essentially agree on the fundamentals. They agree on sort of their picture of the world in the sense that they see same forces. So they agree on the forces that they experience, and they agree on causal relationships between things. And in particular, one of the most striking things that they agree on is on the speed of light. So the speed of light is a fundamental constant of nature. It's equal to 3 times 10 to the 8 meters per second. And this is something that everybody measures, doesn't matter how fast they're moving. So that's kind of weird. I know it's weird because if you're moving towards the light or you're moving away from the light, you're always measuring the same speed. So that's kind of a strange property of relativity. And in particular, what that means, this is kind of the maximum speed limit. Nothing can travel faster than the speed of light. That was kind of the consequence of relativity. And the main sort of important conclusion for us about it is that any influence or information can move no faster than light. So I can't communicate to anyone faster than the speed of light. So what does this mean, for example, in the world? Well, for instance, we're orbiting the sun, so there's our happy little sun, it's glowing, and here we are on our planet, and we're orbiting the sun, right? And the sun is some distance away from us, and were the sun to suddenly disappear, it would take us 8 minutes to find out that someone's left the building, right? We wouldn't know about it right away. The information would have to take some amount of time. How is that information communicated? Well, what would happen if the sun were suddenly gone is that gravitational waves would be created. So there would be like sort of fluctuations of space-time, and these fluctuations missing that sun will propagate out until that gravitational wave would hit us, and then we would start doing something sad. Right? But before that happens, we have to wait for the waves to come. Okay? So the point of relativity is that you cannot actually, so what relativity suggests as far as like the structure of the equations is concerned is that it says there really can't be any influence without fields. So a field has to sort of permeate all of space. And if you perform some sort of change, what you're doing is you're kind of twisting that field, and that field will oscillate, and eventually its influence will propagate out and change what's going on, right? So influence has to happen through fields. That's kind of the main first lesson of special relativity is the connection between influence and field. So we said that influence can't move faster than the speed of light. What actually moves the influence? It's fields. So influence moves with fields. Okay? So what does that mean, for example? It means that, like, you say you can imagine a cell tower sitting here, and here is your cell phone somewhere else. Here it is. It's shiny and new. And in this cell tower is sitting a little electron, and the cell tower basically vibrates this electron up and down. The electron creates a field, and this field reaches your phone, and your phone goes ding because in it is another electron, and that electron feels the field propagating through space, and your phone goes ding, ding, and a new wonderful scratch is created on Facebook, okay?
Go, yeah!
So, what are photons? Aren't they particles that transfer
Okay, let's wait.
light?
You are like at you know, the after we rest. Yes.
Are there electrons in the fields?
Good.
Yeah.
Let's come back to that. No, so the field I'm giving you first kind of the classic picture of relativity. I'm giving you the picture that was developed, let's say, up to the 20th century, more or less. And the fields are classical objects. They're sort of vibrations. So let me show you actually a movie. Our high tech. Oh, it actually went to sleep. Sorry again. Just so we see what I say. I'm not telling you a lie. Someone's made a cool video about it. Must be true because it's on the net.
What is the meaning of those Z's?
Let's not go there.
Yeah, we have to erase it, otherwise we won't see the movie.
I think we'll be fine.
Svet, turn on the light.
Yeah. Okay, good. So let me just show you. So what is this? This is essentially the field. So this is this electron, and it has already field lines connected to it, the electric field, because it's a source of charge. And I'm just going to show you what happens when that electron begins to move. Like I said, it's starting to disturb the field lines, and it's creating a wave, and that wave keeps propagating out, right? So you keep seeing these sort of like lines pulsating in various ways. So here's another same picture. So the wave is created by the electron as it's sort of moving up and down. So it's a cooler version of the picture I drew on the board. So
Question is, what is?
so there's an electric field and a magnetic field, and there's a direction of propagation. Sorry? Someone had a question? Yes.
It's a wave of what?
It's a wave. The deepest question. It's a wave of energy. It's just the field itself waving. People were very confused about that for 100 years or so, right? They thought they were asking, what? Well, wait. Hot.
We don't want to.
Why does YouTube think that this is what I'm going to be interested in? I blame somebody else. I blame somebody else. Okay, good. Lights back on. Okay, great. So that the waves are connected to every single the electric field lines are connected to every charge, and when you shake that charge, you are creating waves in the fields. Okay, great. So now we get to be kind of a pesky theorist, and we get to ask, but what do those rules of the waves look like? What do the electromagnetic equations look like? So what is the structure of the electromagnetic equations? So these are the equations that describe light and describe the way that waves are created. They also describe how magnetic fields work around magnets. They describe how charges move. So what do they look like? Well, they look like the following. They look like changes in the electric and magnetic fields are proportional to charges and their movement. So that's sort of putting into math the picture that we saw. The charge was moving in some particular way, and as a result, it changed the electromagnetic field. And we can ask in this context, like, what does it look like? What are the constraints of these equations, right? Well, the constraints are not very strong. Basically, you can take any blob of charge, maybe a plus charge here, maybe you have some minus charge here, and there are field lines that come out of the plus charges, and they go into the negative charges, and there's some mess. And this blob characterizes the fields, and basically I can move this blob around. Right? The equations don't tell me what the blob is. It basically tells me that all moves of this blob are fair game as long as I don't destroy or create charge. So I can move the blob however I want, but I cannot destroy charge, create or destroy charge. And also I cannot move anything faster than the speed of light.
So is that what describes the field?
Yes, this is what describes the field. So essentially I have like a lot of freedom. Like a blob is a very vague object that can do whatever. Any picture of a blob is fine. The equations, they don't tell me what the blob is or the blob does, besides this very, very kind of minor constraint, right? So the equations by themselves, they have a lot of freedom. They basically allow any blob to exist. Okay? So the input to the equations that describe electricity and magnetism is very complicated. Anything is allowed, basically. So the input is essentially arbitrarily complex. The equations themselves, they don't constrain what I'm allowed to do. As a theorist, I can do whatever I want. I can jiggle this blob however I want. It just tells me how the fields respond. Okay. But now I can be even worse. I can be like a very pesky theorist, and I can be like, yeah, but who said these were the right equations? Right? Maybe I can change those equations. I just have to obey the rules of special relativity. So there's a set of mathematical principles. I'm not going to like tell you what they are, but there's a set of mathematical principles that tell me what special relativity is. And now I can ask, okay, how can I mess with these equations? What can I do to these equations that still respects this principle of special relativity? And it turns out that messing with the equations constrained by the rules of special relativity by themselves gives me a lot of freedom. Actually, it turns out it's not true that electromagnetic waves have to move at the speed of light. They can move slower. So electromagnetic waves can move slower than the speed of light. That's one thing. Also, it turns out that charge doesn't have to be conserved. I can write down some terms which are completely fine with the principles of special relativity, but charge can basically disappear and appear, right? And something that's going to be important for us for later on is that light usually, so maybe I should, with the usual equations, light waves have two components. What do I mean by that? So we saw that in the picture, there's a wave that is oscillating back and forth, and is moving in a particular direction. It turns out that the wave, the electric field, so if this is the direction of movement, so this is the wave moves in this direction, then the electric field has to always be perpendicular to this direction. There are no oscillations of the field in the direction of motion. Which means that if I look from this side, if I'm looking at the wave when it's coming at me, like what I see, say the wave is coming at me out of the board, is I just see a field that can point in different directions, right? It can point up or it can point to the side. It has two separate components, but those are the only two components. So my only choice is the electric field can point anywhere in this plane, And so there are two components to the field. I could specify how much there's field in this direction and how much there's field in that direction. And so that soaks up all the possibilities, right? Now, this too can be changed. If I mess with the equations, suddenly I can get the field to vibrate in the direction of motion. So even this is not true, according to the rules of special relativity. So if I'm a pesky theorist, I could be like, well, my possibilities here, it's a rich world. I could add this, I could add that. Let's just tell the experimentalists, they go look for this. Prove to me that this is wrong, right? Okay, good, so lots of freedom. Questions?
So if charge doesn't have to be conserved, this means that energy doesn't have to be conserved?
No, energy can be conserved still. But let's get to energy, very good. Sure. Charge and energy are separate, but they're very much related in the what about to say next. So you're thinking along the right direction. But here, the equations of electricity and magnetism, they don't explicitly say anything about energy. They only say what the field does in response to the movement of charge. So they all know, the structure of those equations requires the conservation of charge, usually. So basically, though playing around with the rules of special relativity, I don't have to conserve charge. A magical thing is true. I can impose a particular symmetry, which I'm not going to explain, but there's some sort of requirement that I can impose on these equations that forces me to have only two components. And it turns out if I only have these two components, then the wave looks like the way it does, then charge must be conserved. So the usual structure of the equations of electricity and magnetism are such that the fact that there are only two components, the fact that the electric field fluctuates only perpendicular to the direction of motion, is forcing charge.
Okay, so just kind of have to assume that
Right.
to make it true.
Right. The equations otherwise wouldn't make sense. So there's something I can do to those equations, but I don't know where this comes from. I can certainly make my equations into the equations that we see in nature by imposing a certain thing on them, and then the thing that I'm imposing is literally the statement that there should be no more than two components, and that somehow magically is related to charge conservation. Okay, good. It's unclear, where does that come from? Why do they have to have two components? What's wrong with fluctuating in the direction of motion? There's nothing, it doesn't seem to violate any principle of special relativity. Good. All right. So we know that there are waves of electricity and magnetism. That's one set of waves. There's one influence that happens over long distance. And the other one is gravity. So what I want to say a little bit now about gravity, right? So we talked about the fact that there are gravitational waves, right? That space-time is actually curved, and there's a fabric of space-time, and what gravity is kind of warping of this fabric of space-time. So we can ask the same question, what about the gravity equations? What do they look like? How constrained are they? So what do the gravity equations look like? They're called Einstein's Equations, even though it's unclear if he actually came up with them. That's usually what happens in science. What they say is that the curvature of space-time is related, so the curvature of space-time is actually the same as changes. This is actually the same as changes in the gravitational field. So what the gravitational field measures is how far things are from other things. That's actually what it is. What's what it means to have a space-time. is the gravitational field is basically telling you these two objects, how far are they from each other? And when space-time vibrates, the distance between objects changes. That's what the vibration of space-time is. So the curvature of space-time is actually measuring the changes of the gravitational field, how things, the distances change, like how it's kind of getting warped, right? And the curvature of space-time is actually precisely related to energy, which of course is the same as mass by Einstein's famous formula. So mass and energy are the same. So it's proportional to energy and its movement. So the same way that the electromagnetic fields were related to charge and its movement, gravitational fields are related to energy or mass and its movement. So energy and mass deform the space. So you have like some sort of mass sitting somewhere. There's a blob. So again, any blob will do. I have some energy or some mass in this blob. And around this blob, I've created a field. Around this blob, I kind of warp space-time. Looks like this. There's some kind of curvature. And so by moving this blob, I jiggle space-time.
So it's basically energy and mass causing curvature.
Exactly. It's energy and mass causing curvature. In the same way that electromagnetic equations are charge causing charge and movement causing electromagnetic fields. And one of the cool aspects of this, remember that the structure of the equations that Einstein derived are only consistent if energy is conserved. So remember that electricity and magnetism was only consistent if charge was conserved. That means charge could not be created or destroyed. Actually, so this is the first time we asked the question, well, what is fundamentally forcing energy to be a well-defined object? Why is it that energy can never be created and destroyed? Why is it that energy just flows from one system to another? It's actually because in Einstein's theory, it's a requirement. Like the equations of space-time would not make sense if energy were not conserved. So they enforce, basically, the equations enforce the conservation of energy. They force conservation of energy.
Does that mean that the energy then gets transferred?
Yes, it's a movement of energy that gets moved around, but it can never be destroyed because that would be an inconsistency of the structure of these equations. So that's already kind of interesting, right? So we didn't know, like we assumed energy is never created or destroyed, but now we see that, in fact, the equations of gravity are forcing that to be the case.
Well, if we assume them to be correct.
Exactly. So now we can be a pesky theorist and we can be like, okay, so what? Why can't I just change those equations? What's the principle that enforces those equations? And again, it turns out, very similar story. I can mess with these equations. I can add all kinds of terms to these equations according to the rules of just special relativity. So if I want to just obey the rules of special relativity, I can mess with these equations in all kinds of ways. So in the original equations, gravitational waves move at the speed of light. I can mess with that. I can cause the gravitational waves to move slower than the speed of light. I can cause energy to not be conserved.
Same as charge.
Yeah, same as charge. So the structure of the equations is such that, just by the rules of special relativity alone, I can do a lot of damage. I can really mess with the rules of the world, and then I could be like, oh, I'm such a clever theorist, I really screwed this up, energy is not conserved, why don't you guys go find evidence for non-conservation of energy, or something like this, right? So this is what theorists sort of do when they think about the world. They're always kind of trying to tweak the equations. But something very interesting happens here as well. Gravity, just like electricity and magnetism, the gravitational waves also has components, right? So when a gravitational wave goes through an object, let's say a ball, what the ball is going to do is it's first going to squish this way, and then it's going to get squished that way. So it goes like this, and then back, and like this, and then back. So if your gravitational wave went through your head, you'd be like that. Okay? And amazingly, we built detectors that now can measure this. So we've actually measured. There's a detector which is just made of two very, very long arms, and it has very precise measurement of distance using lasers. And all they basically check is for this thing to get a little squished and this one to be a little stretched. That's basically how that experiment works. But again, you see that this thing is essentially, so this is, I'm showing you what happens if the gravitational wave comes out of the board, and it has an orientation, right? It's the same as with the other wave, that if you think about it in a plane, right, you're thinking about how you orient the wave. This, like, stretching can happen in any direction. So it can happen in this direction as well, it can happen in this direction, or it can happen up and down. So it can happen in any direction of space, and therefore, there's again two components. But when I mess with the equations, I always introduce more components. So again, if you insist on there being only two components, suddenly I'm forced into this picture, and I'm forced into energy conservation. So the same structure seems to appear again. Two components in electromagnetic field equations force me to conserve charge. Two components in the gravitational field equations force me to conserve energy. But you could be like, okay, why two components? So this is a mystery that classical physics doesn't explain. Good, let me show you a video since we talked about this experiment. Let me show you a video of the merger of two black holes. So people have, just a few years ago began actually looking for kind of situations where they can essentially, good. So, of course I have to, thank you.
With a simple quiz.
Good, very simple quiz. Okay, so these are two black holes and they're coming together. And on the bottom here, you see there's like a wave. This is what the detector actually measures. It measures this waveform. And from this waveform that it measures, you see this is traveling here. The detector tries to guess what actually it detected. So it has various models that involve complicated dynamics of the surface of space-time and how it twists. And this is showing you what happens, like how space-time bends. And you see that waves of space-time are being formed. So like as these guys collide into this enormous crash, it's a little chirp that you hear in the detector, like they become one big black hole, and a lot of energy comes out in terms of gravitational waves out of that black hole. And it's kind of amazing that this experiment is able to detect this, this sort of thing. Okay. So now, even though this thing was theoretical for a long time, now we actually know that this is a true picture of the world. Okay, good. So that's more or less what I want to say about the structure of relativity. Let me say a few words about quantum mechanics, and then we take a break. Okay, so relativity, we learned there's a lot of room for maneuvering. They're basically, the equations themselves have very little constraints. I can move any kind of blob around, and it's fine. I have equations that tell me how fields respond to me manipulating matter, but it doesn't really tell me what the matter itself is doing, and there are many, many possibilities. Okay. That's my perspective as it feels, right? So now, what about quantum mechanics? So what are the rules of quantum mechanics? How do they look like? And how much freedom is there to mess around? So basically, quantum mechanics was very confusing for a very long time And when people first started developing quantum mechanics, they essentially thought of first in terms of particles. So they basically ignored they assumed that objects don't have a structure, and they just kind of modeled them as points, and it was kind of easier to start. So the idea is that if you have a classical model of some kind of particle, so it's essentially some object whose size we ignore, we're very far away, we don't know what it really looks like on the inside. For us, it's just a point, right? So it's some particle. And the change that quantum mechanics made is that usually particles, we want to know where they are and we want to know how fast they're going. But quantum mechanics said, no, that's not the actual in data that we see. What we see with quantum mechanics instead is this thing.
So what does quantum mechanics tries to describe in the first place?
I'm trying to draw it for you. So quantum mechanics replaces a point particle with an object, which we call psi of x. It depends on the position. What is this object telling me? It's telling me what's the probability of finding a particle in a particular place. So where, let's say, there's a lot of shading, that's where it's very likely to find it. Where there's not very much shading, that's where it's unlikely to find it. So this simple thing is now replaced by this very complicated object, which is called a wave function. And what it says is it tells me for every point, it doesn't tell me what the particle is doing, it's actually just telling me the probability of finding it there. So I'm replacing essentially certainty of knowing that a particle is at some place going in some particular direction with a much more complicated object that is only telling me the probability of finding.
But are we talking about electrons and down?
Electrons, exactly. So an electron, for example, is really something like this. It's a cloud. It's what we call this like an electron cloud. This is one electron, just to make sure that this cloud represents one electron. This is what the probability is of finding that one electron in any particular position. It's kind of weird, but that's how life is. Right? So we said that energy is king, right? We said that energy is really how we define what systems do. So in a classical world, if we had a bunch of particles, right, if we had a classical energy, what we would say is, okay, there's a bunch of particles, there's some picture, they're all moving in some particular direction, let's say. So this is, I don't know, a bunch of particles in this room, and they have some positions and they have some velocities, and to these positions and these velocities, I assign a cost, I assign an energy. So it's some energy that depends on the positions of the particles and on the velocities of all these particles. That's what classical physics is like. What's the quantum analog? The quantum analog is weird. It basically says, you give me the probability, this sort of object that prescribes the probability of finding a particle, and I can assign an energy to that. So the energy depends on this blob, this probability, and the shape of this thing. Each shape is assigned a particular energy. So I'm not assigning an energy to finding the particle somewhere. I'm actually assigning the energy to the probability of finding the particle somewhere.
Hey, Ami,
Yes.
can you tell us about double slit experiment?
I did before.
Oh, you already did, so it's...
Yeah, I'm not going to
3
take
years
like.
ago.
Yeah.
Because this is kind of the origin story of...
Yes, I'm happy to tell you. It's just I can't do everything in one lecture. So for my purposes
It's on YouTube.
today, you know, for my purposes today, I won't. But yeah, if you want, I can tell it to you offline.
There was a whole lecture.
Yeah, there's a whole lecture. It took me half an hour to explain it.
You got a laser pointer. A couple slits.
But so the idea here is that I'm assigning an energy cost to this psi, which depends on the positions of all these different particles. So it's kind of weird. So this is, again, the energy cost is assigned to the probability of finding
Each particle.
each particle. Okay. But if this wasn't weird enough, it gets weirder. Okay, so that's just sort of the basics of sort of the input-output of quantum mechanics. But quantum mechanics has another weird aspect to it, which is very non-intuitive and causes a lot of confusion, including to all the people who do it every day, to all the quantum mechanics out there. And that's the fact that particles don't seem to have separate lives or identities. So if, you know, if I drew like a little animal to represent like a particle, right? If I had like, let's say, one electron and then it met another electron, right? And if they came in contact with each other, what would actually happen is they would form a mutual animal. Many legs and two heads. And I wouldn't be able to tell anymore, because it's not meaningful somehow, which one's the first electron, which one's the second. What I would get is a little beastie like this, okay, that has multiple heads and many legs. It's one object. And if I have like many of these electrons, what I would get is a complicated beastie that has little legs everywhere and heads everywhere. It's one object. So what the shocking thing of quantum mechanics is it changes, if you like, our epistemological, to use a fancy word, notion of the world. And in our classical notion, we think of this as an object and this as a separate object. But in quantum mechanics, there's one wave function for everything, which is really confusing. Okay? So things don't have separate identities. They just kind of merge into these kind of complicated beasties. Now, it turns out that on top of that, in a way that wasn't really understood why, there are two types of kind of particles. There are particles that hate each other and particles that love each other. Okay? So here, let me explain that. So basically, that's another thing that people observe in nature, is that there are two types of particles. There are particles called fermions, in honor of Fermi, who's a famous Italian physicist. And what these particles experience is just constant hate towards each other. They are very territorial. They really need their personal space. So when they form one of these beasties, they really kind of want to stay away from each other. Their little heads are always far apart. I can't tell which one's which, but I can tell that they don't like each other. So these little beasties are what's sitting inside your devices, and that's how your devices work, is these beasties are connected in some long way, and they kind of dance in a funny way, and that dance of these beasties is why your devices work in the way that they do, and they're very much based on the fact that the main objects in your devices, the electrons, they are fermions. So are protons and neutrons, many types of particles, that all of them are sort of hateful of each other. They stay as far away from each other as possible, and when you try to push them together, they're upset. Okay? So that's fermions. The other are called bosons, after Bose, who's a different physicist, and bosons love each other. Basically, the boson lifestyle is they can all happily live on top of each other. All their heads are in the same place, basically. They just make a big love pile. So everybody's sort of sitting on top of each other. So it's just a love pile. So what are bosons? Like, well, the Higgs, for example, happens to be a boson. So photons are bosons, atoms are bosons, so there's certain atoms that are bosons, photons, Higgs, there's lots of different objects in quantum mechanics that really, really love each other. And they're happy to hang out with each other, and they think the more the merrier. Okay? So both are very important for life. You have to have people who value their personal space and people who don't. Okay, good. So let me show you a picture of maybe what it looks like. More realistic based picture of this. Okay. So what I'm showing you here is this is a beastie. It's the probability of finding. So there are two particles here. They both live on an interval, and 0 to 1. And these guys are bosons. Why do I know that they're bosons? They're bosons because they love to be on top of each other. See? They're most happy when the position of one of them is exactly the same as the position of the other. So what this shows you is the position of one particle and the position of the other particle, right? So remember that the quantum wave function is one object, and what it tells me is the probability of finding a particle, one of the particles at x and the other particle at some y, right? And so they have a bump, which is basically preferring both of them to be on top of each other. So you can translate this bump into, they both sit and kind of mostly want to sit in the middle on top of each other. So their x is the same as, the x here is the same as y. This is where the probability is the highest. It's when they're on top of each other. Question?
What causes them to be away from each other if they're always attracted?
Sorry?
Yeah, why does it then collapse into one?
Yeah.
Very good. So typically they have, so if they're very, very, their interactions, there are other interactions that they can have. So typically bosons are made of charged things on the inside, like for example an atom. And so when they approach each other too close, they do actually feel electric repulsion. So, but you're right, if there wasn't for this electric repulsion, they would all just kind of collapse in a big pile, right? That's actually what's called a Bose condensate. So when people were looking for this, that's what causes, if you've ever heard of superfluidity, that's what superfluidity is. Superfluidity is basically when, say, helium atoms are cooled to such low temperatures that their quantum properties come out to play. And when they come out to play, basically all the atoms pile up in this one big, huge bump, and they're all happy together. And as a result of that, they essentially lose the ability to leak energy. So that's why it's called a superfluid. Yes?
In this graph you've got here, so is the z-axis probability?
Yes, the z-axis is probability,
and
right?
each x and y is a separate particle.
Exactly.
Okay.
Right? So this is what it looks like for bosons. They both like to be here. This is maybe a better view, right? They each, like the half, 1/2 is the highest probability. So both of them like to be on top of each other on both of the halves. This is what fermions look like, right? They hate each other. They try to avoid each other whenever they can. So if basically what this tells you is that if one of them is, let's say, at 3/2, the other one is like at 1/4, at 3/4, and the other one's at 1/4. So whereas these guys like to stay in the middle, these guys, on the other hand, their highest probability is to stay as far apart as they can. Meaning, if one of them is at 1/4, which is here 0.25, the other one here is at 0.75. So they stay as far apart from each other as they can. They don't want to be in the same place. This is just actually a picture of a quantum wave for a particle in the box. Okay, good. All right, let's say one more thing and we go to break. Now, why are there bosons? Why are there fermions? Why are some particles bosons? Why are some particles fermions? None of that is clear from the basic quantum rules of quantum mechanics. It's just something that people discover and they know how to put into their equations. But as theorists, we want to ask the question that we keep asking: how constrained is this? Okay, we mess with what are the inputs of the system? And so it turns out that essentially, if I have some classical particle model, then there is a procedure by which I can guess what is a quantum version of this model, such that in the quantum version, if I let's say, take the classical limit of that model, I get back to the classical model that I started off with. So this is a procedure called quantization. I'm not going to explain what it is, but the idea is that basically the reason I'm saying this is that the input of the classical particle model is actually the same as the input of the quantum particle model, because there's a flow that takes me from each classical model to a quantum model. So what are the kinds of inputs that we put into a particle model? Well, basically, the input of a particle model is the relationship between particles. So we can have two particles, and they can be some distance apart, say r. And the way I prescribe what happens in this model, remember I told you, is like I need to tell you the energy, right? So what I need to do is I need to tell you their relationship. I need to say, how much energy is it to keep them some distance apart? So for example, if the energy depends on distance like this, they hate each other, right? Because if they're close to each other at small r, they want to go further away to large r, so this is they hate each other. So particles that have this kind of a relationship of energy, they hate each other. On the other hand, I can have a relationship of energy that goes like this. So if I have a relationship of energy that goes like this, it's the opposite. I lower my energy by going to smaller distance, which means they love each other. But I can do whatever I want, right? For example, I could do something like this, where I have R and I have the energy, and it could go like this. So this is what you would call a romantic comedy, right? They hate each other if they're far away, but you get them hanging out close to each other, and then suddenly they're in love. This is a sort of romantic comedy. So it's sort of hate out here when they're not too close, and then suddenly if they become close, they just want to go and form it. Okay, but the point is that the input is whatever curve I want to write down. So quantum mechanics doesn't tell me anything about this curve. I can just fantasize whatever kind of relationship, whatever landscape I want. They can have love, they can have hate, they can have whatever they want, and there's no, yes, question.
Does this mean that generally, as a temperature, I know you're talking about the helium molecules, does this mean that generally as temperature lowers, particles demonstrate more of their quantum, like?
Right, because essentially quantum states are very delicate, precisely because their kind of information there is only one wave function, and the second that the environment talks to them too much, then like the information from this quantum state begins to leak very efficiently into the environment. So it's very important that the environment is as quiet as possible. Right? That's exactly right.
Thank you.
Okay, so the bottom line is that the rules of quantum mechanics are pretty loosey-goosey. There's a lot of things we can do, and there's not a lot of constraints by themselves. And we saw the rules of special relativity by themselves are also pretty loosey-goosey, right? Good. That's a good place to stop. Then we'll combine them after a bit of a break. Okay, shall we start?
Yep.
Okay, great. So we're going to combine quantum mechanics with relativity. So recap.
Easy.
we found that with just special relativity, we had a lot of freedom. Basically, we just had fields, and we had either charge or energy as the thing that determines those fields, but the charge and energy sources, they could be whatever the heck we wanted, right? We could have some distribution of charge. It was a blob. We could move it around however we wanted. If we were talking about gravitational fields, the gravitational fields come from energy, right? And we said that any energy configuration was possible. So there was a lot of freedom. We could mess with equations in all kinds of ways. With quantum mechanics just by itself, we also saw that there was a lot of freedom. We have, let's say, two particles, and we can determine their relationship, right? Like how they react as we separate them with some distance. They can be attracted to each other, they can be repulsed, they can be first attracted, then repulsed. I mean, it could be however complicated that we want. Nothing about the rules of the game tell us that like there's a lot of restriction. We have a lot of freedom. But now we're going to try to combine quantum mechanics and relativity and figure out what are the rules of the game. So the first surprise, right, is that particles and fields are the same. So fields are made of particles. So that was a huge surprise. Even people who loved quantum mechanics, like Bohr, who invented quantum mechanics, he was happy to have electrons, for example, have this quantum wave function that tells you about the probability of where the electron is. But he thought the electromagnetic field was like this beautiful thing. He said to Einstein, "Don't touch that. That's some beautiful object. I really love it. Don't quantum mess with it." Okay? And Einstein said to him, "It doesn't make sense to have quantum electrons but not have quantum version of electricity and magnetism because the theory doesn't jive." And so Einstein was the first person, in fact, to say that there are objects called photons, insist that they really exist, and that those objects carry an energy. So he had basically two very famous equations. One is E equals mc squared. This equation he didn't technically write down first, but I think he was the one to actually the first to kind of insist on it being really physically true. So what does this equation say? It says that within the electromagnetic field are packets of energy. So the electromagnetic field is in fact a love pile of photons. That's what it is. Remember we talked about photons or bosons. They like to kind of pile together. They like to create something nice and smooth. And when they pile together, they actually create the field. So the field is made out of these individual chunks, which are the photons. And the energy of the photon depends on their wavelength, which we use the letter lambda. It depends on their wavelength. There's the speed of light. And this h is a new kind of constant in nature. It's Planck's constant. How much is it? 6.6 times 10 to the minus 34 joules seconds. So everything is in units of energy and point in time. So this is a fundamental constant of nature, just like the speed of light. It's the quantum constant. It creates quantum stuff. And the idea behind this formula is saying something that we sort of experience in life. We see colors around us, right? We see various vibrations of the electromagnetic wave. We see blue, we see green, we see all these different colors. And where do these colors come from? Why do we see these colors? We see these colors because for each color there's an energy cost. Remember I was telling you that the way we understand modern physics is we say for each configuration, for each type of thing, there's an energy cost. So before this equation, nobody really understood where colors come from, but it turns out the colors are really just coming from the fact that photons hit our eyes, and these photons have certain wavelengths, and the shorter wavelengths are bluer, the longer wavelengths are redder, and when these photons hit our eyes, they carry a certain energy. and they rearrange molecules inside of our eye. And that's why we see blue, or we see green, or we see red. So this all comes from this equation. So our entire experience of color is from this equation. So a very important thing, we like to look at the world. The world's colorful. Color has an energy associated. Okay, so that's kind of the first surprise. So maybe I'll show you, let me show you a little picture. This idea. Let's see. Let's show this first. Okay. So the projectors.
Надо думать, что да.
Oh. No, it thinks it's plugged into something.
Maybe you need to.
It's not like that.
It's on.
It's on?
Yeah, yeah.
Yeah, it's buzzing. Yeah.
Oh yeah?
Good.
Can you unplug it and plug it in?
Do we need to power it up and down?
Yeah, I guess.
So if fields are made of particles, it means that the gravitational field is also made of particles?
Yes, we'll talk about that. It's made out of the graviton. Very, very deep name.
And there are spaces between those particles which do not experience nothing, that's true.
Well, it's kind of more, the particles are sort of, I'll show you a picture which hopefully will explain it. Like, it's a bit tricky. They're not kind of particles in the way that
Or they're also fields of...
they're basically, the particles are, they carry a certain energy. You should think of them as sort of packets of energy, but they're not actually localized in any one place. They're kind of smeared across the wave because they're associated with the wavelength and not like a location.
So they're also almost like a probability
Yes, yes.
blobs.
They're probably blobs. So, should we, something's happening and then it didn't happen. Did it happen?
Here we go.
Oh, it went very quiet.
I turn it on again.
Okay.
Zaz. There we go.
Good.
Oh,
That's-
we can dance, we can do the vertical dance.
Right.
Just choreograph our movements.
So, okay, hopefully it'll show up.
No, one sec. One sec.
Bow. Okay, great. There we are. Okay, good. So let me erase. Okay, so here's a picture of kind of what I mean by this formula is in pictures. So we're used to light, right? Going through a prism. You've seen this dark side of the moon thing. It splits the prism splits the light into colors, and the different colors are actually different frequencies. So when we say that there is an electromagnetic wave, which is what light is, and inside of it, it contains different frequencies, what we're really saying is that we have different numbers of photons. So, for example, if the wave is very, very red, that means that there's a peak around like the frequency red. There are many photons that have the red frequency and less of the blue frequency, and so on. So basically, the different colors are really just the intensity of the different colors is telling me how many photons there are of that frequency inside of the wave. So the wave is built up of sort of like little bricks, right? There's like 1 photon, 2 photons, 3. So some frequency, if it's very high, that just means that that color is very strong. If there are very few photons of a different frequency, that means that that color is very weak inside of the wave, okay? So quantum mechanically, this is the surprise, is that actually this smooth object is made out of these little chunks. Okay. And so what I want to say, how does this relate to, how does this relate to, visible light? Well, for example, the hydrogen atom, right, is some electron blob, and if I hit it with light, it absorbs light and it changes shape. And if I hit it with light again, it absorbs energy and it changes shape. So essentially what we're seeing when we're like seeing a particular object have a particular color is that it can absorb certain energies and change its configuration. And so that tells us what the energy is, right? And of course, as I said, different wavelengths correspond to different colors, right? So long wavelengths are red and very short wavelengths are blue, right? And there's a whole spectrum of radiation. That spectrum of radiation from radio, which is very, very long wavelength, all the way to like X-rays and gamma rays, these are just different photons of different energies. Which is why when you have a microwave oven, where's Lana? Okay, it doesn't hurt you. Okay, this is very low energy. Okay, okay, this is physics. On the other hand, gamma rays which are radiation, right? We talk about gamma rays when there are radioactive elements around it. X-rays and gamma rays, they have very short wavelengths, therefore they carry a lot of energy and they're very dangerous, right? Question.
What about mobile phone?
Mobile phone,
Where are they?
Microwaves,
I mean, mobile phone is mostly radio.
Radio and
I mean, probably has a little bit of leakage, but it's not going to leak all the way.
What about if these devices are broken?
Broken. They don't have mechanisms to generate that kind of energy.
What about 5G?
You need radioactive elements.
What about 5G?
Doesn't matter how many G's it is. More G's doesn't move you this way. Thank God. Okay. All right. Good. So very good. So that's all I'm going to say here. Thanks. Lights, please. All right. Good. All right. So the electromagnetic field is actually made up of these these photons. Now I want to explain what that actually means as far as how things interact. So now imagine that I have two electrons, let's say electron 1 and electron 2. What is the fundamental interaction? Like what's going on, like beneath the hood? We're now saying that the fundamental ingredients of the electromagnetic field are these things called photons. Also, according to relativity, so we're trying to combine. We have now this quantum object, the photon, we have this quantum object, the electron, and we have to have them interact. Well, according to the rules of relativity, they can only interact at some particular point of space-time. They can't interact at a distance, right, because this will violate the rules of relativity. Something can only interact at a point. It's not that something can happen here and suddenly something else happens far away. So the only interaction has to be local. So photons and electrons have local interactions. So what does it mean for two electrons to feel each other? Well, what happens is that this electron is actually sending a photon, announcing its presence to the other electron. It receives that photon and it's like, sure, dude, here's a photon back. And then this guy sends a photon back. And then this one sends a photon back. And then so they're constantly tossing a football to each other. Like they're basically telling each other about each other by this constant exchange of a photon. And remember we said that many, many, many photons is the same as a field. So all of this picture, if you just look at the lifestyle of this guy over here, what he thinks is happening is that he's just kind of seeing a smooth field approximately. He doesn't see this guy. After many, many, many photons pile up on him, he just experiences motion inside of the field. So the field is an emergent phenomenon, right? It's not there in the actual equations of quantum relativity. It emerges because the experience of the electron is to see many, many photons hitting it. And those many, many photons, we said, together build up the field. Right? Does that make sense? All right. So this becomes the electron field. So that's the first kind of thing, right? Now, the other thing that we said, for example, we said all bosons, they have this, they're all the same, right? You can't tell the difference from one photon and another. was kind of a mystery. The rules of quantum mechanics kind of discovered this, but there was no real sense of like, why is that true? But now when we combine quantum mechanics and relativity, we understand that that's true because all photons are same because they're all just quantum fluctuations of the same field. Are the same because they are just quantum fluctuations of the same. Okay, so that's what happens when you think of quantum mechanics and relativity together, right? Moreover, what is the quantum? So so that means that the field now has a quantum meaning. So what is the kind of quantum meaning of the field within this picture? Well, the quantum meaning of the field is that this is some point in space and time when this photon was created and then went and traveled onwards. So really in the quantum code, so quantum mechanics is code, right? I told you this sort of before, but basically what that means is that the quantum language is actually very similar to the language of code. And within that code, the electric field, let's say, which depends on position in space, just tells, essentially, is a line of the code that allows me to create a photon in some position in space and time. So the electric field creates or destroys photons. That's what the quantum version of a field is. So it's kind of an object that allows me to create and destroy photons. So electric field acted here to create the photon here. An electric field acted here to destroy the photon. Then an electric field acted here to create the photon. Then another one acted here to destroy it. So that's basically the way that this works. And so the first shock, as I said, is that fields are made out of particles, and the fields themselves create these particles. That's basically what the fields are in the quantum language. And the next surprise is that actually, as someone asked, Rodrigo, there's actually a field for electrons as well. So there is a quantum field for electrons. So what is the quantum field for electrons? It's something, I don't know, let me call it psi for an electron. It has the same label X. It also can create or destroy an electron at some point. So the same way that I have an electric field, which is something we know from the classical picture that can create and destroy photons, there's a quantum field that can create and destroy electrons. And now we can ask, okay, but why have we heard about this? Why did we have a field, an electric field, and no one's ever heard of this? And the reason is that these guys are bosons, and they like each other, and they pile up on each other, and they create this field, whereas electrons hate each other. They never build up a classical field. They basically, to build up a classical field, you need many, many, many things that kind of pile up on each other and make a smooth object. So electrons are fermions, and therefore there's no classical analog to this. But it's kind of cool that in the quantum relativistic language, these objects are the same. So this is basically the same. In the code, in the quantum relativistic code, these are the same objects. There's a field for every particle that there is in nature. There's a field which can create and destroy that particle. And that also explains why all electrons are the same. They're all the same because they're just the quantum fluctuations of this field. Okay, so there's a kind of unity. We don't distinguish between particles and fields anymore. You combine quantum mechanics and relativity, there's only one thing. You can use the particle language or you can use the field language, they're all the same. So that's the first kind of amazing unity.
Is there a notion of energy there?
Yes, there's a notion of energy because processes that create and destroy particles of a particular type, cost a certain energy.
So is that field of electrons going to be significantly more energetic, so to speak?
Yes, in a sense, because in a physical process, very good, you have exactly right intuition, because photons are massless particles, so it doesn't cost a lot of energy to create them. Almost anything creates like a wave of many, many photons. But electrons have a mass, right? And so by E equals mc squared, I need a lot of energy to actually create them.
Yeah.
Exactly. Okay, so now we want to talk a little bit about the structure. So what is now the input? So for example, suppose I wanted to describe, let's say, our world, and maybe I want to talk, so here I had two electrons. What if I want to describe kind of the two ingredients that we're aware of, like that I hope many of you know. So there are electrons, and let's say they're protons, right? And electrons can interact with each other, protons can interact with each other. What is now the input of this theory of electrons and protons? Right, we talked about the fact that before, inputs could have been any blob or any kind of curve or anything. What is the data that fully determines, uniquely determines, the theory, quantum theory of electrons, protons, and photons interacting? What are the parameters of that theory? Well, it turns out that the interactions, like we said, for the electrons, they happen locally. Right? So there's a photon that comes off the electron, and it turns out that the only thing I need to know is the probability of throwing out this photon. That probability is called alpha in m, and it's in nature approximately 1 over 137. It's just a number. This is a probability, just a number. So the parameters of this model is the mass of the electron, the mass of the proton, and this number. That's it. And as a theorist, if you were to say, well, both the electron and the proton, if I were to treat them as point particles, the proton's not. As I'll explain, it's actually made up of other stuff. But if I ignore this, there are no other parameters that the model has. And I can't add any more parameters. The rules of quantum relativity tell me that this is it. There are only 3. So we went from an infinity, because any blob was possible or any curve was possible if you just had special relativity or you had quantum mechanics. When you combine the two together, it's just 3 numbers. Okay? Well, let's keep going. What about the rest of the world? What about everything else we know about? Well, it turns out that particles have a characteristic that sort of characterizes their lifestyle. It's called their spin. Particles have something called spin. What is spin? Spin is a mathematical property. It is the response of a particle to rotation. Okay? In a sense, you could sort of think of like little particles as kind of little spinning balls, and they rotate and they have kind of an angular momentum, but it's not really correct to think about it. Like it's sort of like a model you could think about it because you have to picture something, but really kind of it's not really that they're turning or spinning. It's more like their response to rotation. So the spin of particles turns out because of math, because of the properties of rotation, which is a mathematical object, can have only certain labels. It can be 0, it can be a half, it can be 1, it can be 3 halves, it can be 2, and so on. That's it. There's a discrete list of numbers. So basically, half things like odd numbers over 2 or all integers, positive integers. Those spins, the spin of the particle, more or less uniquely characterizes its lifestyle. So spin 0 particle, for example, is the Higgs. The spin 1/2 particles are electrons, protons, neutrons. Spin 1 particles are photons and other force carriers, as I'll explain. Spin 2 is the graviton. It's the quantum of gravity. So once I know what the spin is, the shocking thing about quantum mechanics and relativity is when I now have to prescribe the interactions of objects here, these various particles of different spin, my options are completely limited by math. It's no longer that I can do whatever the heck I want. I have to actually look up at math tables, and the math tables tell me what to do. So quantum mechanics together with relativity is so restrictive that mathematical objects determine all of the things I can write down. So let me kind of give you a sense of how this works. By the way, I should say a few more things before we go on, because again, so I said, for example, that these guys are spin 1/2 and these guys are spin 1. We'll notice that these guys are actually fermions, they hate each other, and these guys are bosons. And of course the Higgs is a boson, because that's what they say on the news. And the graviton is also a boson because it makes up a field. So that was not clear before, but when you combine the rules of quantum mechanics and relativity, it turns out that spin integer are always bosons. It's just consistency conditions of the math. Whereas spin, like odd over 2 are always fermions. Again, just math. It has to do with the properties of quantum relativity. Moreover, massless particles are very special. Because if you're massless, then you have to move at the speed of light. Like, for example, a photon. So let's say the photon's moving in this direction. And then the spin can only point, it turns out, either in the direction of the motion or opposite the direction of the motion. There's only 2 options. Again, math tells you that. But these are the 2 components. These are literally the 2 components of the electromagnetic wave. So remember, we were like, oh, if there are only 2 components, then like the equations of electricity and magnetism can take a certain form and charge has to be conserved. Well, quantum relativity forces you into having 2 components, and therefore by consistency charge must be conserved. So math says that charge is conserved now. Because the only rules that you can write down, which are consistent with mathematical properties of quantum mechanics and relativity, is that. Now the same thing happens, so this was for the electromagnetic field, but the same is actually true for gravity. So the graviton is a massless particle, and again, it can only have spin in the direction of motion or spin in the opposite direction of motion. That's what it turns out to be math. But remember, we said that that's again 2 components, right? And we said that if you have 2 components, then Einstein's equations have to have the form that they do, and they enforce that energy is conserved. So when you take the quantum version of gravity, the only way to have a consistent theory of quantum gravity is to have energy conserved. So if a child asks you, why is energy conserved? Why can energy not be created or destroyed in our world? The answer is quantum gravity. Quantum gravity says that there can only be 2 components, and it turns out that that creates the entire structure of Einstein's equations. Einstein's equations follow from this. That's what's amazing. There's no more freedom. It's a completely crazy situation, right? Where suddenly, just by that property, I get so much, right? Okay, good. So let me say a little bit more about the rest of the structure of our world, and I think that will be good enough for today. So I want to explain a little bit about like what are the other kinds of fundamental ingredients that make up our world and how we build a theory of all these ingredients, right? So I'll keep this picture here. Okay, any questions before I know it's been...
Do you know other missing sort of pieces? Like, what's number 4?
Yeah, all of Europe is looking for number 4. So number 4 is a very special particle, and if it exists, it implies a symmetry which is called supersymmetry. It basically says it cannot exist, so in the same way that spin 1, the photon, its existence forced you to have charge conservation, and in the same way that the existence of the graviton forced you to have energy conservation, the existence of this particle would force there to be a pairing between any boson and any fermion. So it's a weird thing that we don't see in nature. It would mean that the electron has a boson partner called the selectron. The photon would have a fermionic partner called the photino, and so on. So it's a model where every particle has kind of a partner with the opposite love-hate. So if for any particle that hates itself, there will have to be a particle that loves itself. We do not see this in nature, but people were very much excited about this possibility that this is what nature is like, because people have seen this and this and this and this, and they were like, okay, maybe we can see this too. But so far, nature doesn't seem to have such a particle, nor evidence for this kind of symmetry. But that's the point that I'm trying to say. Do you see, every time you add a particle, you're actually forcing some kind of constraint on the world. That's kind of the message I have to say. Okay, so let me just finish up and tell you about the cast of characters of our actual world and a little bit about the parameters of our world. I'm going to only include what I think are kind of the important characters for our particular lifestyle. So how do you build a model now? How do you build a model of the world? So I say that everything is super restricted. So what you first is you start with your spin 1 particles. So again, it turns out that these are what people call the force carriers. So they're bosons and they can basically build up a field. Now how do I figure out how they interact? Well, essentially, it turns out that they can only interact with themselves and with other things according to mathematical tables. So there is an object in math called a Lie group. Doesn't matter what it is. I can just tell you what a group is. A group is basically a bunch of elements. So it's a bunch of elements linked, listed by some property and some law of how to multiply them. So some multiplication table, basically, of these elements. Mathematicians categorized all of them. There's some kind of, basically you could look it up. They solved the problem of having a bunch of elements with certain kinds of multiplication tables. They're just abstract objects that exist in math land. So for example, there are the weak interactions. The weak interactions cause radioactive decay. They cause the fusion that powers our sun. The weak interactions happen to be 3 spin 1 particles. So I say 3 spin 1 particles. They're interacting with each other. I say, okay, what do I do now? Well, I look up in a math book and I say, is there a Lie group that contains 3 degrees of freedom, basically? And the answer is yes, there's only one. So if I have 3 spin 1 particles, it's an object called SO3. Doesn't matter what it means. It means basically rotation of 3 things. But it's a math object. So I'm more interested that, obviously I'm more interested that you see that, the structure of the laws of nature has completely changed. It's not that I can do whatever I want. I just kind of have to look up in math tables all the time. So that's the weak interactions. Then there's the strong interactions. They bind things into protons and neutrons. They bind nuclei. They contain 8 spin 1 particles interacting with themselves. And it turns out that that's a unique, if I look up in a math table and I want 8 objects to kind of interact with, there's another group. It's called SU3. It's basically the rotation of 3 complex things. Again, it's a table. There's no freedom. If you tell me 8 of them interact together, there's only one structure that I can impose on that thing. If I have the photon, that's the electromagnetic, which is only 1 spin particle. Well, first, by the rules of this math table, there's again a unique group. It's called V1, and it says there's no self-interactions. So the photon can just not interact with itself. That's the rules. So once I have my force carriers, basically it's a list of spin 1 particles and which spin 1 particles talk to which spin 1 particles. So if 3 of them talk to each other, this is my only option. If 8 of them talk to each other, this is my only option. And then there's 1 of them which can't have self-interactions. So I start with spin 1, and then I add spin 1/2. And by the time I add spin 1/2, I add all my characters that I will need to describe our world. And again, my life is completely limited. So I add to this spin 1/2. So for example, I have my electron. It turns out that the electron participates in the weak interactions. By the laws of math, it can't do that by itself because of the structure of this object. It has to have a partner. It's called the neutrino. They're together. They talk to each other through the weak interactions. Again, this is the property of this weak group. It's the property of math. Then it turns out that there are quarks that make up the proton. I can't have an up without a down because, again, the weak interaction tells me, but in the math tables, that I can't have one without the other. So the weak interactions, the fact that up and down are exchanged with each other by the weak interactions, tells me that for an up, there must be a down. It's property of the math table that characterizes this object. Then I have, because of the fact that the quarks, they feel the strong interactions, it turns out that there are 3 of these. So their quarks are labeled by another label called color, and traditionally it's red, green, and blue. This is just a label that people imposed on it for reasons that I'll explain in a moment. So there must be 3 of them. Why 3? Because this has a 3, basically. Again, it's some property of math that it has to be like this. And now I can determine the charges of all these objects. That's what tells me how the photon sees them. And it turns out that if the charge of the electron is -1, if I'm in units where that's true, then the charge of the up has to be 2/3, and the charge of the down has to be -1/3, or else the structure is not self-consistent. I have no choice. These are the charges of the quarks. Again, it's all math tables. This completely changes like how we did physics for hundreds of years. So basically, at the end, like, as long as I'm talking about objects which I think are fundamental, but they don't have any internal structure, then there's no more freedom. Basically, every single model that I can write down has only a finite number of parameters. So let me just finish by telling you what are the parameters of our world. So the quarks, the up and down quark, the strong interaction binds them together. There's a up, up, down, and the red, the green, and the blue, they kind of talk to each other. Red, green, and blue together is white. And so people say that whereas these guys have color, when they get bound inside of a proton, you can't see the color anymore because red plus green plus blue is white. So it's kind of a construction. Again, it's just a quirky physics way of labeling mathematical properties. The point is the proton has to have charge +1 because of the charges of these quarks, which we said were determined by math. And then the neutron, which is another important particle in making up the world, where again this is red, green, and blue, or any other combination which includes the different colors, but they're always one red, one green, one blue. This has to have charge 0. So the entire world, our entire world is actually the only parameters that enter into our world is the mass of the up, the mass of the down, and the energy associated with the strong interactions, which you can think of as approximately the same as the mass of the proton times c squared. So it's the binding energy. So when these quarks are bound together to make a proton, most of the energy comes from the binding. It doesn't come from the masses of the individual quarks. So even though, we're used to E = mc squared, really most of our weight is coming from the other way around. It's the energy of binding that's creating our mass. It's not because these quarks have mass. So that's a parameter. These parameters determine all of nuclear physics. Like all the structure of all the various nuclei. So all of nuclear physics is determined by these 3 parameters. To this, we already said we add the mass of the electron and this alpha E and m, which is 100/137. Together, this determines all of the periodic table. This is the only input to the periodic table are these numbers. So they determine all of chemistry and therefore all of us, all of life in biology. All the complexity of our world, for the most part, is determined just by these numbers. That's it. There's no freedom. That's it. Now, to this, it turns out if you want to understand radioactive decay and the fusion in the sun, you add another parameter, which has to do with the weak interactions. Okay? And so now this, in addition to this, you now understand all fusion and fission. And finally, let's give Newton his due. The only other parameter of our world where we started with Newton today, and it's the strength of gravity. That's it. These parameters determine everything we know, basically, in our entire world. Why? Because quantum mechanics and relativity is so restrictive that it becomes essentially math, and the number of inputs goes from anything down to 1, 2, 3, 4, 5, 6, 7. Less than the 10 Commandments. Okay, I think that's what I'm saying.
But how consistent they are?
So if by consistency you mean how much wiggle room do I have?
Yeah, do they explain everything?
They explain everything, and I can't add any other ones. I can measure them. I don't know what they are, of course. I have to get them from experiment. But with these ingredients, there's nothing else I can add. That's it. Because, as I said, everything else is kind of determined by math.
Mm-hmm.
So it's really an amazing change in the way we do the work.
Yeah.
Yeah.
So what role does, I don't know if the word is entropy or decay, play in the way things behave in the real world? All of these constants and waves.
So entropy and decay, so I guess let's see, by decay you mean just like rotten food kind of decay, right? What do you mean by
that
decay?
too? No, I meant in terms of when you were describing the way that things, propagate in space
Yes.
via waves.
Yes.
These waves are not constant, are they?
No.
Okay. And so, you talked about color, you talked about time, you talked about all these things, and the way they behave in the real world is that as things expand, they lose and extend and slow down.
Right.
Uh-huh.
Right. So if you're talking about the features I was talking about, as I was showing you in the beginning about how waves move, the motion of those waves are determined by the fact that the photon is a spin 1 particle. That's it. Those are the only words I have to say. Amazing. Like just saying that determines the quantum field that creates this particle and determines basically the equations that govern electricity and magnetism. They're completely determined statements. Amazing. The same thing with gravity. It's a spin 2 particle, and everything we know about gravity just is determined by that. Yes?
So are gravitons, are they just theoretical?
They're theoretical at this point.
And others are mathematics?
So of everything I've told you, well, so first of all, we've now seen experimentally gravitational waves.
For sure.
We don't think that it's consistent to have, just a classical theory of gravity, because but as I was trying to explain, I feel as a theorist that the circumstantial evidence is very strong. Why? Because as a theorist, I'm allowed to mess with the equations. And typically, if I'm allowed to mess with equations, nature messes with the equations. That's basically our experience as theorists. So if I can write something down and nature doesn't realize that, it's either because nature has different principles, right? But it's never because, nature just chooses not to do it. It never happens. So my bias as a theorist is to tell you the following: energy is conserved, quantum gravity. Because if the theory were classical, I could write down all kinds of terms that wouldn't conserve energy. I could change the number of components in the gravitational field. I could do all sorts of things to mess with the equations, but I don't see that.
So it's just like theory is pushing you to
Yes.
think that there is most likely graviton.
Right. But we will never probably detect the graviton. It's just too weakly coupled as a quantum object.
What about like exotic matter type of, and like dark matter? Where does it come from?
Dark matter is not in this table, but
What do you think?
but it's probably a particle or a set of particles. I don't think we'll have to change the laws. Like, again, we will discover that the particles are spin 0, spin 1/2, spin 1, or whatever, and people build models of that. So I've built models of dark matter. It's okay. You build a model of dark matter, it works with the data. I mean, it's not that the data is not constraining enough to tell me that whole approach is wrong. So I don't expect dark matter to be something that doesn't fall in the grander catalog of what it presented.
So it shouldn't be like another force in the whole.
I mean, it could have its own dark forces, but again, they would be like new spin 1 particles that we just happen to have not discovered.
Are there some interesting unknowns? Like what's...
Yeah, there's a lot of unknowns. So that, remember when I wrote my little blurb, I was going to talk about all the problems. I decided that we have enough problems, so we should stick to the positive today. Maybe I'll come back and I'll tell you all there are many things that are unknown. So this is all very good, but for example, it turns out that we don't really know how to use these rules to simulate the world. We also don't quite understand how to have a quantum version of our universe. We don't know how to write down. We understand if fluctuations of gravity are weak, which is what mostly happens, we know pretty well how to describe, small fluctuations of gravity. So quantum gravity with small kind of fluctuations works fine. Given recent understandings, black holes probably also work fine, but nobody really understands. So in the sense that we know that black holes are quantum objects in gravity, we kind of understand how to describe them generally. There are specific things we still don't know, but we have no idea how to describe a quantum version of the larger universe, like the universe as a whole with gravity. Yes.
So Andy,
Yes.
there has been a number of theories of quantum gravity, like loop quantum gravity and so on.
Yeah.
There is a number of them, you can't really tell which one's correct.
That's not true.
Well,
I mean,
within limits, right?
Within limits, yeah.
So how does this work into?
Into this picture, or?
How does this picture correspond to Let's say loop quantum gravity.
Okay, that requires me to tell you another, it's a whole separate lecture. I'm happy to come back and tell you about this because it doesn't, because the loop quantum gravity people I think incorrectly, because we have evidence like from other things that they think incorrectly. They basically kind of want to create a kind of quantum geometry and stitch things together in terms of some discrete kind of structures and hope that it creates some smooth continuum, but there are technical reasons why they're wrong.
So this and that don't work together.
That they don't work together, yeah. I have to give you a completely separate understanding of how we actually deal with these objects, because the problem is that the real truth, so this is the good news, that there's all these things, we classified them, yay, but the bad news is we don't actually know how to take these objects and turn them into real laws for evolving the world. And that's related to sort of that.
So that is basically the next step.
It's the next step.
Specifically, loop quantum gravity doesn't work.
Yeah, it doesn't work because of something called holography. I have to explain what holography is. It's a separate.
So which one do you like? Which one do you propose is the most?
I think it's kind of misrepresented in the media. The problem with quantum gravity, like I have to explain to you what black holes are like. The problem with quantum gravity is that in all of this description, we talked about local things happening in space and time. In quantum gravity, space and time cannot really have a well-defined meaning. Like they have to be emergent, approximate properties. And so then we have to, so we have evidence for such objects mathematically. So that's why I'm pretty confident that we mostly understand black holes, for example, but we don't understand how to apply that for
Because you have such a discrepancy between these forces, and gravity being so weak that you cannot measure it practically.
No,
it's a small system on Earth without just,
I have to explain more structures. It's because quantum gravity is very different from, it's very different from this kind of, maybe I should explain it to you using the following kind of experiment. So when you use very high energy probes, if you have a system without gravity, then those high energy probes, the higher the energy, the shorter the wavelength. That's the formula that I was writing down. So high energy means very high resolution, which means in everything I've talked about so far, like you get more and more information as you crank up the energy. You're basically resolving things on shorter and shorter distances. That's how the collider, the collider in Geneva is basically a fancy microscope. But when you add gravity into the mix, the opposite happens, because if you pump too much energy in a particular location, it forms a black hole and it kind of obscures everything that happens. So what it really means is that locality itself is messed up. So that's kind of maybe the best way I can,
That's it?
That's it.
Yeah, I was thinking that if you add to time, energy, and space, you add imagination, you get a good Terry Pratchett model.
Yes.